Sometimes our problems with resistor and voltage circuits get even too complicated for our rules for series and complex series and parallel circuits. And then we have to turn to Kirchoff's laws to solve that problem.
Circuits. And to do that, we're going to talk about Kirchoff's laws, which are basically some laws based on conservation of charge and conservation of energy. They're not difficult to understand. They make physical sense to us, I think, but they do create some fairly complicated problems. So let's first understand what they are. There are two of them. One of them is the junction rule. The junction rule says the sum of currents entering a junction, right? Our junction here is A, must equal the sum of the currents leaving. That makes good sense, right? Think of our pipe metaphor. If I have water flowing through here, that water has to leave either through there or through there, and they have to be equal. I can't have more water leaving a junction than's coming in, and vice versa. So we can write here, we want to turn this into an equation. What we're going to do is end up solving, coming up with, for a complicated circuit, 2 or 3 or 4 equations, and then solving them for 2 or 3 or 4 variables. So we come up with an equation here. Basically, it says I1 is equal to I2 plus I3. Okay. In this case, 11 is equal to 7 plus 4. And like I said, this is just like a pipe junction. So that's one of the two Kirchhoff's rules. The second Kirchhoff's rule is the loop rule. And the loop rule says that the sum of changes in voltage around any closed loop must be 0. In other words, as I go around here, from any given point back to that same point, I have to find myself back at the same voltage. And that makes sense too, right? We could do all sorts of magical stuff. If I could go around here and I start at 17 volts and end up at 23 volts and then back at 29 volts, that wouldn't make sense to us. So we're basically saying that the circuit has to make logical sense. We can think about that in terms of elevation here. Again, a nice little metaphor. So I have a ground wire. It jumps up to 18 volts with my battery. Resistance lowers it to 17, then the resistance lowers it to 5, then the resistance lowers it to 0, and I'm back at 0, jumps up to 18, and so forth. So that's the loop rule in concept. Again, not difficult in concept. And you can see that this, the internal resistance of the battery is relatively small. The external load resistances are large. So we talked about that. So how do we create an equation here? Well, you go around the loop, okay? And you note at each change what that voltage change is, okay? So here we could start at our 0 point. We're going to go up our EMF, that's our voltage, right? EMF is actually, a voltage of the battery is the EMF minus the change in voltage across the internal resistance. Again, don't worry too much about that. We're not going to worry too much about the internal resistance in batteries. So we can sort of assume the battery is going to jump us up 18 volts. And then as we go around the loop, well, how much voltage am I losing here? Well, I can use Ohm's law, right? V equals IR. And that's going to be the voltage drop there, right? And that becomes that term. It's going down because it's going through a resistor. The battery makes it go up. There's a positive number down through the resistor. I come down here, again, V equals IR. I want to know what that voltage drop is. IR. I is the same for all of these because it's a series circuit. And then finally, we do another IR there, and we set that equal to 0. Okay, so there can't be any overall change in the voltage.